Chapter 3 Advanced Machine Learning Techniques. 3.1 Ensemble Methods. Ensemble methods are a foundational concept in advanced machine learning that involve combining several models to solve a computational intelligence task more effectively than any single model could on its own. These methods leverage diversity among the models to achieve higher accuracy and robustness in predictions. The overarching goal of ensemble methods is to pool the predictive powers of multiple learners, thus reducing the risk of choosing an inferior single model and improving generalization over unseen data. The theory underpinning ensemble methods rests on the premise that a group of weak learners, when aptly combined, can outperform a single strong learner. This can be likened to the wisdom of the crowd, where collective decision-making often leads to more accurate results compared to individual judgments. In machine learning, weak learners are individual models that perform slightly better than random guessing. Ensemble methods target the aggregation of these individual models to form a strong learner, which categorically boosts performance metrics such as accuracy, precision, and recall. One core aspect of ensemble methods is the manner in which individual models are generated and combined. There are primarily two ways of constructing ensembles: bagging and boosting. Bagging, or bootstrap aggregating, involves training multiple models in parallel, each on a random subset of the training data. These models are typically of the same type, and a key feature of bagging is that the subsets of training data overlap because they are sampled with replacement. Bagging is particularly effective in reducing variance, thereby addressing overfitting that single predictive models may experience. Boosting, on the other hand, is a sequential process where each model is built upon the errors of the previous ones. The models are weighted according to their performance, and those that predict incorrectly have their weights increased. This ensures subsequent models focus more on the difficult cases that earlier models misclassified. Boosting techniques are noted for their ability to reduce both bias and variance, thus enhancing the predictive strength of the ensemble. Another important aspect of ensemble methods is the strategy used for aggregating the predictions of individual models. For example, in classification tasks, one common technique is majority voting, where each model casts a vote for a class label, and the label with the most votes is the ensemble's final output. This simple yet powerful method ensures that errors from individual learners, assuming they are independently and identically distributed, are likely to be outvoted by correct predictions. In regression tasks, ensemble predictions often involve averaging the results of individual models. This reduces the overall model variance without making significant sacrifices in terms of bias. The concept of model diversity within ensembles should not be overlooked. Ensuring that individual models are sufficiently diverse is crucial for the success of ensemble methods. If models are too similar, they will likely make identical errors, which undermines the entire premise of an ensemble. Therefore, it is essential to promote diversity, either through manipulating the training data, as in the case of bagging and boosting, or by using different types of models altogether. Sometimes ensemble methods include models that are purposely undertuned to introduce diversity and reduce correlation between their errors. Random forests are a concrete example of an ensemble method based on decision trees. In a random forest, many decision trees are trained, each on a different sample of the data and with a different subset of features considered at each split. This creates a collection of diverse trees, and their collective decisions, typically via mode of the output in classification or mean prediction in regression, represent the random forest's output. The strength of random forests lies in their ability to maintain high accuracy even when some data features are not relevant, which makes this method both powerful and resilient to overfitting. A newer generation of ensemble methods includes stacking or stacked generalization. In stacking, predictions of individual models become the input for a higher-level learner. The base models are trained first, and their predictions are combined into a new dataset that is used to train a final meta-learner. This model aims to learn how to best combine the predictions from the base-level models, thus refining ensemble decisions. Stacking can be complex and requires careful design to avoid overfitting, but when implemented correctly, it can yield performance benefits over non-ensemble methods. It is crucial to recognize the implications of using ensemble methods in terms of computational resources. Since multiple models need to be trained, these techniques can be computationally intensive. The trade-off is the potentially significant improvement in predictive performance. However, practitioners must balance the computational cost against the benefits, especially in scenarios with constraints on resources or where real-time predictions are required. The evaluation of ensemble methods must be as rigorous as any other machine learning approach. Cross-validation is often used to assess the performance of ensemble methods, ensuring the evaluation is not biased by the specific way the data is partitioned. Model interpretability is another factor that may be impacted by ensemble methods. While single models might be easily interpretable, especially in the case of decision trees or linear models, ensembles can complicate interpretation. Strategies for understanding and explaining ensembles, such as feature importance measures, are an active area of research. In practice, ensemble methods have seen widespread application across various fields. From financial risk assessment to medical diagnosis, the blending of multiple models has allowed for better predictive performances and more robust decision-making processes. The constant evolution of ensemble techniques and their underlying theory is a testament to the vibrancy and innovative nature of the field of machine learning, offering practitioners a potent arsenal of tools to tackle an ever-widening array of challenges. As machine learning continues to evolve, ensemble methods remain a cornerstone of the discipline, ensuring that the quest for improved algorithms and better predictions presses forward with unrelenting momentum. 3.2 Dimensionality reduction techniques. In the realm of blockchain technology, machine learning can be utilized for various purposes, such as fraud detection, price prediction, and network optimization. However, blockchain datasets often suffer from high dimensionality, which leads to challenges in computational efficiency and model accuracy. Dimensionality reduction techniques are essential in pre-processing stages to address this issue. These methods simplify the inputs without sacrificing the integrity of the data, enabling machine learning algorithms to perform more effectively. In this section, we will discuss various dimensionality reduction techniques and their applications in the context of blockchain technology. The most basic form of dimensionality reduction is feature selection, where the goal is to identify and use a subset of the original features in a dataset. Feature selection can be conducted through various statistical methods, such as correlation coefficients, chi-squared test, or mutual information measures. By keeping only the most relevant features, models can potentially improve in performance and interpretability. Within blockchain analysis, feature selection helps in identifying the most significant transaction attributes that contribute to trends or anomalies. Another fundamental technique is feature extraction, which transforms existing features into a lower dimensional space. Principal component analysis, PCA, is a widely used method for this purpose. PCA operates by finding the orthogonal projection of the data onto a lower dimensional subspace, where the variance of the projected data is maximized. For blockchain transaction data, PCA can reduce hundreds of dimensions into a few principal components, which can then feed into other machine learning models for further analysis. This allows for the efficient handling of vast amounts of data without overwhelming computational resources or risking model overfitting. Beyond PCA, there is linear discriminant analysis, LDA, which is particularly useful for supervised learning tasks. LDA attempts to find a linear combination of features that characterize or separate two or more classes of objects or events. In the context of blockchain, LDA can be used to identify characteristics that differentiate between legitimate and fraudulent transactions. By projecting data onto a lower dimensional space where the classes are well separated, LDA can improve the accuracy of classification algorithms. Another technique, independent component analysis, ICA, assumes that the features are mixtures of independent sources and attempts to unmix them. ICA is useful in blockchain when the goal is to find hidden factors that influence the system. For instance, in analyzing the prices of cryptocurrencies, ICA can help identify underlying components, such as market sentiment or economic indicators affecting price fluctuations. T-distributed stochastic neighbor embedding, TSNE, is a nonlinear technique specifically designed for high-dimensional data visualization. It works well on datasets where PCA might fail to reveal meaningful patterns due to the nonlinear relationships between features. TSNE has been used to visualize the transaction networks in blockchain, revealing clusters of addresses and transactions, which can be integral in detecting fraudulent behavior or understanding the flow of tokens across the network. In situations where the dimensionality is extremely high and traditional methods are infeasible, autoencoders, a type of neural network, can be employed for dimensionality reduction. Autoencoders are designed to learn an encoding for a set of data, typically for the purpose of dimensionality reduction, by enforcing a bottleneck in the network through which the data must pass. Autoencoders have been used in blockchain to compress transaction data before submission to a predictive model, preserving the essential information while significantly reducing the input size. Manifold learning is another set of techniques for nonlinear dimensionality reduction. Methods such as isomap, locally linear embedding, LLE, and spectral embedding operate under the assumption that the high-dimensional data lie on a low-dimensional manifold within the high-dimensional space. This is helpful for blockchain data, since it can capture complex relationships between transactions that are not immediately apparent. Manifold learning is considered when analyzing highly intricate patterns beyond the reach of linear methods like PCA or LDA. When dealing with temporal data, such as blockchain transaction time series, dimensionality reduction must take into account the sequential nature of the data. Techniques like dynamic time warping, DTW, allow for comparing time series by means of an elastic transformation of the time axes. This can aid in grouping or comparing different periods or sequences of blockchain transactions, which is useful for identifying trends or repetitive patterns. For high-dimensional categorical data, which is common in blockchain, multiple correspondence analysis, MCA, is an appropriate choice. MCA is an extension of PCA for categorical variables, transforming them into a set of continuous variables and revealing the underlying structure in the data. This can be particularly beneficial when analyzing user or contract types in blockchain, where transactions often include various categorical attributes that are deeply interconnected. Finally, random projection is a dimensionality reduction technique suited for data with very large dimensions and is based on the Johnson-Linden-Strauss lemma. By projecting the original data onto a lower dimensional subspace using a randomly generated matrix, random projection preserves distances between the points with high probability. This method can be incredibly fast and has the advantage of requiring very few assumptions about the data. It's particularly useful in blockchain when quick, approximate solutions are necessary, especially in systems where computational resources are limited, such as edge computing devices participating in a blockchain network. These techniques collectively offer a toolkit for addressing the curse of dimensionality in blockchain datasets. Choosing the appropriate dimensionality reduction method depends on the specific characteristics of the data and the goals of the machine learning task at hand. Effective application of these techniques can drastically improve the performance and accuracy of machine learning models employed in the blockchain domain, ultimately leading to more reliable and insightful outcomes. 3.3 Advanced Neural Network Architectures. The development of advanced neural network architectures has been a critical factor in the rapid progression of machine learning capabilities. Neural networks are structures inspired by the human brain, designed to recognize patterns and solve complex problems. Early designs were relatively simple, but today's architectures are far more complex and capable. This section will delve into several advanced neural network architectures that have been influential in broadening the applications of machine learning. Convolutional neural networks, CNNs, are one of the most influential architectures designed for processing data with a grid-like topology, such as images. A CNN automatically and adaptively learns spatial hierarchies of features from input data. This ability is facilitated by the convolutional layers that apply filters to the incoming data, which helps to reduce the number of parameters and computational complexity. The architecture of CNNs usually includes layers like rectified linear units, ReLUs, for nonlinearity, and pooling layers for downsampling. These networks have been particularly successful in image recognition tasks and are extensively used in computer vision applications. Recurrent neural networks, RNNs, represent another significant advancement in neural network architectures. Unlike feed-forward neural networks, RNNs have connections that form directed cycles, enabling them to retain a state or memory. This feature makes RNNs well-suited for processing sequences, such as time series data or natural language. RNNs can process inputs of different lengths and can predict future events in a sequence, which is beneficial for tasks like language modeling and translation. However, traditional RNNs suffer from issues like the vanishing or exploding gradient problem, which affect their capacity to learn long-range dependencies. Long short-term memory networks, LSTMs, are an enhanced version of RNNs, specifically designed to overcome the limitations related to learning long-range dependencies. LSTMs include memory cells that can maintain information for long periods, gate mechanisms that regulate the flow of information into and out of the cells, thereby mitigating the vanishing gradient problem. These design features allow LSTMs to capture long-term temporal relationships, making them highly effective for many tasks in sequential data processing, including speech recognition and predictive text input. Another important development in neural network architecture is the Generative Adversarial Network, GAN. GANs consist of two neural networks, the generator and the discriminator, which are trained simultaneously through a competitive process. The generator learns to create data that is indistinguishable from real data, while the discriminator learns to differentiate between real and generated data. This adversarial process continues until the generator produces plausible data. GANs have become popular for their ability to generate synthetic data that closely resembles real-world data, with applications ranging from art and design to the generation of realistic training data for other machine learning models. Attention mechanisms, particularly the transformer architecture, represent a leap forward in sequence modeling tasks, predominantly in natural language processing. Transformers eschew the recurrent nature of RNNs and instead rely on attention mechanisms to weigh the influence of different parts of the input data. By doing this, they can process all parts of the sequence simultaneously, which greatly improves efficiency and scalability. Additionally, the use of self-attention allows the model to focus on different parts of the input sequence when predicting different parts of the output sequence, demonstrating remarkable effectiveness in machine translation and text summarization. Graph neural networks, GNNs, are designed to work with data that is represented as a graph, consisting of nodes and edges. Traditional neural network architectures assume that all inputs have a regular structure, like rows in a dataset or pixels in an image, but GNNs can handle irregular inputs by incorporating the connection information between entities. This makes GNNs suitable for phenomena represented in non-Euclidean domains, such as social networks, knowledge graphs, and molecular structures. They are especially adept at learning the interdependencies between elements within the graph structure. The concept of neural architecture search, NAS, represents another front in advancing neural networks. NAS is a subset of AutoML, automated machine learning, where the goal is to automatically design neural network architectures optimized for a specific task. This is achieved through a process that searches for the best performing architecture within a predefined space, assessing numerous configurations. By using algorithms such as reinforcement learning or evolutionary approaches, NAS can discover network architectures that often outperform manually designed models. Increasing the depth of neural networks led to the creation of deep belief networks, DBNs. DBNs are generated by stacking layers of unsupervised networks called restricted Boltzmann machines, RBMs, on top of each other. After pre-training each RBM, the layers are fine-tuned through supervised learning. This layered structure allows DBNs to learn a hierarchy of features from in-labeled data, which can then be used for classification or other predictive tasks. Their ability to perform well, even with a limited amount of labeled data, is beneficial for applications where labels are scarce or expensive to obtain. Capsule networks, CapsNets, have been proposed as an alternative to the traditional CNNs by addressing some of their limitations. CapsNets consist of groups of neurons, known as capsules, which apply dynamic routing algorithms to encode not only the probability of the existence of features, but also their spatial hierarchy. This approach to handling spatial relationships and pose information makes CapsNets more proficient in recognizing objects from different viewpoints and in reducing the need for large data augmentation during training. Although still an area of active research, capsule networks hold promise for robust pattern recognition in complex scenarios. Finally, the integration of neural networks with reinforcement learning has led to the emergence of deep reinforcement learning, DRL. DRL algorithms combine the capability of deep neural networks for feature representation with reinforcement learning's decision-making capabilities. This powerful combination has been demonstrated in teaching agents to achieve superhuman performance in complex environments, such as playing Go or video games. DRL models continuously interact with their environment, learning to maximize rewards through trial and error, demonstrating significant potential in robotics, autonomous systems, and various control tasks. The exploration of advanced neural network architectures contributes significantly to the advancement of machine learning as a field. These architectures enable the handling of more complex data types, improve learning efficiency, and solve problems that were previously inaccessible to machine learning paradigms. As research continues to evolve, it is expected that new architectures will emerge, each with unique capabilities and applications. The current state of neural network development paints an optimistic landscape, where complex problems across various industries stand to benefit from these intelligent systems. 3.4 Transfer Learning. Transfer learning is a powerful approach in the realm of machine learning and artificial intelligence, where knowledge acquired during training in one type of problem is reused as a starting point for addressing another problem. This technique takes advantage of the fact that certain features or patterns can be relevant to multiple tasks, allowing for more efficient learning and often leading to enhanced performance on tasks with limited data. Transfer learning is particularly useful in situations where the cost of data acquisition is high or where labeled data is scarce. The core concept behind transfer learning emanates from the observation that humans apply knowledge from past experiences to solve new problems more efficiently. In a similar fashion, transfer learning enables a pre-trained model, one that has been trained on a large dataset for a certain task, to be repurposed for a related but different task. For example, a neural network trained to recognize objects within photographs may have learned valuable transferable features that can facilitate medical image diagnosis, despite the domain shift. There are several methods of transfer learning, but one of the most common involves fine-tuning a pre-trained model. In this method, a model that has been trained on a large and diverse dataset, such as ImageNet for image recognition tasks, is repurposed by making slight adjustments to its weights and biases. Fine-tuning allows the model to retain general feature detectors from its original training, while adapting to the specifics of the new dataset and task. This often requires only tuning the final layers of the network, where task-specific features are learned, as opposed to the earlier layers, which capture more general, reusable aspects of the data. Another approach in transfer learning is the use of feature extraction. Here, the earlier layers of a pre-trained model are used to transform new data into a richer feature space, in essence using the pre-trained network as a fixed feature extractor. The output of these layers becomes the input for a new model or a simple machine learning algorithm that is trained on the target task. This method is particularly advantageous when the new dataset is small, preventing the effective retraining of a large, complex model without overfitting. Transfer learning is effective not only in computer vision tasks, but also in natural language processing, speech recognition, and many other domains. In natural language processing, for example, models pre-trained on massive corpora of text such as BERT or GPT serve as bases upon which more specialized models can be built, tailored to tasks like sentiment analysis or question answering. This allows the models to benefit from the rich semantic representation developed from the pre-training before adapting to the nuances of the new task. One significant benefit of transfer learning is the reduction in required computational resources. Training machine learning models from scratch demands significant computational power and time, particularly for complex models like deep neural networks. By leveraging a model pre-trained on a similar task, one can significantly reduce both the time and the computational load necessary to achieve competitive results, making advanced machine learning accessible to a broader range of users and organizations. Transfer learning also contributes to a reduction in the need for labeled data, which is often costly and time-consuming to obtain. By transferring knowledge from a pre-trained model, data efficiency is improved, often requiring less annotated data for the model to achieve high performance. This is pivotal in domains where data is rare or expensive to label, such as medical imaging, where expert annotation is required. Despite its advantages, transfer learning is not without challenges. When transferring knowledge from one domain to another, one must consider the issue of domain adaptability. If the domains are too dissimilar, the transferred features may not be relevant, or worse, may be misleading. This scenario is known as negative transfer, and it highlights the importance of assessing domain compatibility before applying transfer learning. Strategies to mitigate negative transfer include domain adaptation techniques, which aim to align the feature distributions of the source and target domains. Furthermore, the decision of what elements of a pre-trained model to transfer is critical. This includes choosing which layers to retrain, which to freeze, and whether to alter the architecture of the model. Careful consideration is required to balance the retention of useful, generalizable features from the pre-trained model and the need to learn specific features of the new task. This balance is nuanced and may require empirical testing and validation to optimize. The success of transfer learning has inspired more elaborate techniques, such as meta-learning, where models are designed to learn how to learn across tasks rather than learning the tasks themselves. This takes the concept of transfer learning to a higher level by training models that become more adept at adapting to new tasks with minimal data. As we continue to explore the boundaries of transfer learning, it is clear that it will remain a key tool in the machine learning practitioner's arsenal, enabling more efficient and effective models across an increasing array of applications. The continuous development and research in the field of transfer learning are leading to more sophisticated and efficient methods of exploiting pre-trained models. One such development is the concept of zero-shot and few-shot learning, where models are capable of making predictions on data from classes they have not explicitly been trained on. By incorporating an understanding of context and relationships between classes learned during pre-training, these models demonstrate the potential of transfer learning to enable models to generalize to new tasks with little to no additional data. Overall, transfer learning represents a crucial paradigm shift in machine learning, one that encourages efficiency, practicality, and the broad applicability of machine learning models. As data continues to grow in volume, variety, and complexity, the ability to transfer and repurpose knowledge will remain instrumental in overcoming the challenges of building models capable of understanding and acting upon the vast information landscape. While transfer learning simplifies the task of applying machine learning in various domains, it also underscores the necessity for thoughtful and strategic model development and training to reap the full benefits of this technique. 3.5 Generative models. Generative models constitute a class of machine learning algorithms that are used for unsupervised learning. They function by learning the joint probability distribution of input data, which enables them to generate new instances that could plausibly come from the same distribution as the training data. These models differ from discriminative models, which are designed to learn the boundary between classes of data rather than the distribution of data itself. In essence, while discriminative models are apt at classifying data into predefined categories, generative models excel at producing novel content that shares statistical properties with the original dataset. One of the primary applications of generative models is in the domain of image generation and editing. For instance, they can be employed to generate realistic human faces, objects, or scenes that do not exist in reality. These capabilities are particularly valuable for tasks such as video game environment creation, film special effects, and the generation of training data for other machine learning models. They can also be utilized for data augmentation, which involves creating new training examples from existing ones, thereby enhancing the diversity and quantity of data available for training other models. A critical aspect of generative models is their capacity to deal with high-dimensional data. High-dimensional data, such as images, sounds, and texts, present significant challenges due to the so-called curse of dimensionality, which refers to the exponential growth in complexity with the addition of each dimension. Generative models approach this challenge by finding and learning the underlying structure within the data, allowing them to capture essential features and patterns with fewer dimensions, effectively reducing the complexity of the data for analysis and processing. Deep learning techniques, including neural networks with multiple layers, are often the backbone of generative models. The introduction of deep learning has significantly advanced the field, leading to the development of models like generative adversarial networks, GANs, and variational autoencoders, VAEs. These models use deep neural networks to learn complex, high-dimensional probability distributions and have been shown to generate high-quality, realistic outputs that are often indistinguishable from real data. Generative adversarial networks, or GANs, represent a transformative approach to generative modeling. A GAN consists of two neural networks, a generator and a discriminator. The generator network learns to produce artificial data, while the discriminator network tries to distinguish between real and generated data. The two networks are trained simultaneously in a competitive manner, where the success of one network's outputs implicates a refinement in the other's performance. This adversarial process continues until the generator produces data that the discriminator can no longer reliably classify as real or fake. Variational autoencoders, on the other hand, are a type of generative model that learns the distribution of input data in a way that allows for the easy sampling of new instances. A VAE comprises an encoder that compresses the data into a lower dimensional representation, and a decoder that reconstructs the data from this representation. The process involves optimizing a cost function that takes into account both the accuracy of the reconstruction and the divergence of the learned representation from a prior probability distribution, thus ensuring a balance between fidelity and variation in the generated data. The training of generative models is computationally intensive, requiring significant resources in terms of both hardware and time. High-quality generative models often necessitate the use of graphics processing units, GPUs, to perform the numerous calculations involved in training deep neural networks. Additionally, these models typically require large datasets and numerous training iterations to fully capture the intricacies of the data distribution. This process can be further complicated by issues such as mode collapse, where a model might learn to generate only a limited subset of the possible outputs, failing to represent the full diversity of the input data. Despite these challenges, generative models have made headway in various fields beyond image and video generation. In natural language processing, for instance, they are instrumental in the development of models that can generate coherent and contextually relevant text, used in chatbots, automated translation, and content creation. In the realm of drug discovery, generative models can propose novel molecular structures that might lead to new medications, expediting the initial stages of drug development. Moreover, generative models hold potential in the improvement of privacy and security, particularly through techniques such as differential privacy. By generating synthetic datasets that preserve the statistical properties of a given dataset without including actual data points from it, generative models can allow for the sharing of data insights without compromising individual privacy. This capability is crucial for sectors like healthcare and finance, where data sensitivity is a significant concern. Continuous advancements in generative model architectures, training strategies, and their integration with other machine learning techniques are likely to extend their applicability. Researchers are focusing on developing models that can achieve higher fidelity and variety in their outputs, require less data for training, and address current limitations like training stability. The field is an exciting and dynamic aspect of machine learning, driving progress in various domains by opening up new possibilities for creative and functional generation of data, insights, and solutions. Generative models represent a fast-evolving side of machine learning, with new approaches and architectures frequently emerging. Their versatility and capability to generate new data that is similar to real-world data make them invaluable tools across numerous industries. As these models become more sophisticated and accessible, we can expect their impact to grow, transforming the ways we interact with machine-generated content and leaving a significant mark on technological progress and innovation. The ongoing research and practical applications of generative models will undoubtedly continue to shape the landscape of machine learning for years to come. 3.6 Natural Language Processing, NLP. Natural language processing, NLP, is a critical domain within machine learning that bridges the gap between human communication and computer understanding. It involves the application of algorithms and mathematical models to enable computers to process, interpret, and generate human language. The primary objective of NLP is to allow computers to understand text and spoken words in much the same way humans can. This broad field encompasses various tasks, including language translation, sentiment analysis, speech recognition, and entity recognition. One fundamental aspect of NLP is parsing, where the structure of sentences is analyzed to understand the grammatical organization. Parsing enables NLP systems to decompose text into pieces that align with grammatical rules and extract meaning. High-level parsing involves recognizing the sentence's subject, predicate, and objects, while lower-level parsing may involve recognizing parts of speech, such as nouns, verbs, and adjectives. Accurate parsing is essential for the subsequent tasks involved in NLP, such as sentiment analysis or language translation. Machine translation is another pivotal application of NLP, where the aim is to automatically translate text or speech from one language to another. Historically, this task was approached with rule-based systems, which were limited by the need for extensive manual coding of language rules. However, modern NLP utilizes deep learning models, such as sequence-to-sequence neural networks, to learn these rules from large datasets, delivering more accurate translations. Notably, these models can retain context over longer passages, which is a critical improvement over previous methods. Sentiment analysis is the process of determining the emotional tone behind a series of words. This is useful for understanding the attitudes, opinions, and emotions expressed in online conversations. Sentiment analysis allows businesses to track brand and product sentiment in customer feedback, enabling them to better understand their market. This application of NLP deploys classification techniques to assess the sentiment of text data, categorizing it as positive, negative, or neutral. By leveraging deep learning techniques, sentiment analysis can be refined to detect subtleties and nuances in language. Entity recognition, also known as named entity recognition, NER, is a procedure where an NLP system identifies and classifies key elements from text into predefined categories. These categories can include names of people, organizations, locations, expressions of times, quantities, monetary values, and more. NER is critical in many NLP applications, such as information retrieval, question answering, and content summary, because it can quickly distill critical information from large volumes of text. Another advanced area within NLP is co-reference resolution. Here, the task is to find all expressions in text that refer to the same entity. For instance, in a body of text, the terms the president, he, and the leader might all refer to the same person. Understanding and connecting these references are essential for building a coherent understanding of the text. Co-reference resolution leverages both syntactic and semantic clues to build links between pronouns and the nouns or names they refer to. Conversational systems, including chatbots and virtual assistants, are also a significant focus within NLP research and development. These systems aim to interact naturally with users, responding to queries and carrying out tasks through textual or spoken dialogue. Building such systems involves integrating various NLP techniques, including natural language understanding (NLU), natural language generation (NLG), and dialogue management. The current success of conversational systems owes much to improvements in machine learning algorithms and the vast amounts of data available for training. Text summarization is a process where NLP systems generate a short and coherent version of a longer text document. The goal is to capture the main points and convey them as concisely as possible. This can be achieved through extraction, where sentences are selected and pieced together to form a summary, or abstraction, where new sentences are generated to express the main ideas. Text summarization technology benefits users by sifting through large amounts of data and presenting information in a digestible form. Automatic speech recognition, ASR, is yet another area where NLP has made considerable advances. ASR technology converts spoken language into text, potentially serving as an interface for other NLP applications, such as translation or question-answering systems. Current ASR systems leverage deep learning techniques and have reached high levels of accuracy, making them effective for real-world applications such as voice-activated control systems and dictation software. The integration of NLP within search engines has dramatically improved how information is retrieved online. By better understanding user queries, search engines can return results that are more relevant to the user's intent. Aspects of NLP such as semantic search, which involves understanding the contextual meaning of search terms, have played a crucial role in achieving this. Moreover, NLP facilitates the handling of unstructured data, such as text on web pages, enhancing the indexing and retrieval process. Finally, in the continuously evolving landscape of NLP, it is evident that new challenges and opportunities emerge as the field progresses. The integration of NLP with other machine learning domains, such as computer vision, opens new frontiers for interdisciplinary applications. Combining text data with visual information can lead to more sophisticated artificial intelligence systems capable of understanding context across different data forms. The future of NLP holds substantial promise for advancements across industries, with ongoing research propelling the field forward, enabling more nuanced and complex interactions between humans and machines. 3.7 Computer Vision Techniques. Computer vision is a field of artificial intelligence, AI, that enables computers and systems to derive meaningful information from digital images, videos, and other visual inputs, and make actions or recommendations based on that information. It is akin to imparting a level of human sight to a machine. The evolution of computer vision techniques has played a critical role in the expansion and capabilities of machine learning, particularly as we enter an era heavily reliant on image and video data. The cornerstone of computer vision lies in image recognition, which is the process of identifying and detecting an object or feature in a digital image or video. This task is conducted through machine learning algorithms that are trained on a set of sample images. Initially, these algorithms were simplistic and could only detect basic patterns or colors. However, with advancements in technology, they have evolved to identify complex shapes, textures, and objects with high accuracy. Feature extraction is a fundamental technique used in computer vision. It involves reducing the amount of resources required to describe a large set of data accurately. When analyzing an image, instead of examining every individual pixel, feature extraction algorithms focus on identifying the most noteworthy elements, mapping intricate details that distinguish one object from another. This proves to be essential for tasks such as facial recognition, where the subtle features of an individual's face must be captured decisively. Convolutional neural networks, CNNs, have revolutionized the field of computer vision. These deep learning algorithms are specifically designed to process pixel data and are structured in a way that reflects the organization of the visual cortex in humans. CNNs consist of multiple layers of convolutions with nonlinearity and pooling layers, followed by fully connected layers. The convolutional layers serve as automated feature extractors. They filter an input image to produce feature maps that summarize the presence of detected features. This robust framework makes CNNs highly effective for image classification, object detection, and image segmentation tasks. One of the key strengths of CNNs is their ability to learn hierarchical feature representations. The layers closer to the input image learn to recognize simple features like edges and colors, while deeper layers in the network interpret complex features, enabling the understanding of high-level content within an image. Through backpropagation and various optimization techniques, like stochastic gradient descent, the weights of the neurons within these layers are continuously adjusted to minimize the error in prediction, improving the accuracy and reliability of the model over time. Object detection is another critical area within computer vision, going a step beyond classifying images to locating specific objects within the image frame. This is achieved through strategies such as region proposal networks or single-shot multibox detectors that scan an image and generate potential bounding boxes around objects. These candidate regions are then classified. Object detection models must strike a balance between speed and accuracy, and are vital in real-world applications such as video surveillance, autonomous driving, and robotics. Image segmentation is a process that involves dividing an image into multiple parts or segments to simplify or modify the representation of an image into something more meaningful and easier to analyze. Segmentation algorithms partition an image at the pixel level, with the aim to group together areas with similar attributes, such as color, intensity, or texture. This technique is particularly useful in medical imaging, where precise delineation of organs or lesions can assist in diagnosis and treatment planning. Pose estimation is a computer vision task that infers the posture of a person or object from image data. It has applications in various fields, from animation and gaming to sports analytics and physical therapy. By using a collection of algorithms, a computer system can detect human figures in images or video and predict the orientation of joints and limbs. This involves not only identifying individual body parts, but also understanding the spatial interconnectivity between them, posing a complex challenge for machine learning models. Another computer vision technique is visual relationship detection, which involves not only recognizing objects within an image, but also identifying the relationships between them. For example, this might mean detecting not just the presence of a person and a bicycle, but understanding that the person is riding the bicycle. Understanding visual relationships adds a layer of context to the analysis, making the outputs of computer vision systems more nuanced and detailed. This is important for systems that need a deeper level of understanding of the scene, such as those used in autonomous vehicles and assistive technologies. Depth estimation, which is the process of determining the distance from the sensor to objects in an image, is an important ability for creating three-dimensional representations from two-dimensional data. This is particularly significant for applications that depend on accurate spatial measurements, such as augmented reality or robotic navigation. Techniques such as stereo vision, where information from two cameras is used to triangulate depth, or structured light, where a known pattern of light is projected onto a scene, and deformations of this pattern are used to calculate depth information, are commonly used. The mastery of computer vision techniques requires an interdisciplinary understanding of machine learning, neural networks, signal processing, and statistics, among other fields. As technology evolves, we witness the continual improvement of algorithms and the development of new methodologies that broaden the scope of what computer vision can accomplish. These developments will not only foster improvements in existing applications, but also enable entirely new functionality across various sectors of industry, healthcare, security, and entertainment. Through rigorous research and innovation, computer vision continues to be a dynamic field at the forefront of artificial intelligence, shaping the way we interact with the digital world. 3.8 Time series analysis. Time series analysis is a critical aspect of machine learning that deals with the temporal ordering of data. It is used to predict future values based on previously observed values. Unlike other types of data, time series data is sequentially dependent, meaning that observations in a time series have a natural temporal ordering. This dependency challenges traditional machine learning algorithms, which generally assume that individual observations are independent of each other. Therefore, time series analysis requires specialized techniques that account for the innate structure of the data. The first step in time series analysis typically involves making the sequence of data points stationary. Stationarity means that the statistical properties of the process generating the time series do not change over time. This is crucial because most time series forecasting methods assume or require stationarity to make accurate predictions. In practice, a time series can be made stationary by removing trends and seasonal effects. This can be done through various methods such as differencing, where the difference between consecutive observations is calculated, or transformation techniques like logarithms, which can help stabilize variance. After stationarizing the data, it is common to explore the time series through visualization. Plotting the data can help detect patterns, trends, and seasonal effects that might not be evident in raw numerical data. It can also give insights into potential anomalies or outliers that could affect the modeling process. Visual scrutiny is an essential diagnostic tool that aids in appropriately choosing and tuning forecasting models. For instance, autocorrelation plots can help identify the lag until which the data points are linearly correlated with each other, which is pivotal in choosing the correct parameters for certain models like the ARIMA model. Another key element of time series analysis is the decomposition of data. This process separates the time series into several components, typically the trend, seasonality, and residual components. The trend shows long-term progression of the data. The seasonality shows repetitive patterns due to seasonal factors, and the residuals are the leftover variations after accounting for trend and seasonality. Decomposition can be performed using methods like moving averages for trends and the classical decomposition method for seasonality. Understanding these components is necessary for creating accurate models and forecasting. One of the most common statistical methods used for time series analysis is the autoregressive integrated moving average, ARIMA. ARIMA models are flexible and can capture a host of time series patterns. The model consists of three main terms: autoregression AR, differencing I, and moving average MA. The AR part involves regressing the variable on its own lagged, past values. The I indicates that the data values have been replaced with the difference between their values and the previous values, and the MA part involves modeling the prediction error as a linear combination of error terms occurred contemporaneously and at various times in the past. In addition to ARIMA, there are other methods such as exponential smoothing and seasonal decomposition of time series, STL. Exponential smoothing captures trends and seasonality through weighted averages, where more recent observations are given more weight. The STL method provides robustness against outliers, allowing the decomposition into seasonality, trend, and residual components using LOES, locally estimated scatterplot smoothing. Each method has its advantages and is selected based on the specific characteristics of the time series data at hand. Machine learning also introduces more complex algorithms for time series analysis, such as state space models and recurrent neural networks, RNNs. State space models, like the Kalman filter, represent time series observations as a set of latent states evolved over time following a probabilistic model. These are particularly useful in scenarios where the time series data is multivariate. On the other hand, RNNs, and in particular long short-term memory (LSTM) networks, have proven very effective in predicting time series data. They can learn long-term dependencies and model sequences of arbitrary lengths, making them ideal for complex time series forecasting. For multivariate time series analysis, techniques that consider multiple related time-dependent variables, vector autoregression (VAR), and vector error correction models (VECM) are employed. VAR is a generalization of the ARIMA model for dynamic systems where interdependencies between multiple time series are significant. VECM, another extension of the ARIMA model, is useful when dealing with non-stationary, co-integrated variables. These multivariate models capture the linear interdependencies among multiple time series and are imperative when multiple streams of temporal data influence each other. It is also critical to evaluate the performance of time series models. This involves using various metrics such as the mean absolute error (MA), mean squared error (MSE), or the Akaika Information Criterion (AIC) for model selection. Cross-validation techniques for time series differ from those used for other types of data due to the sequential nature of the data. A common approach is time series split cross-validation, where the dataset is partitioned into training and test sets in a chronological manner, ensuring that the model is validated on data that has not been used in its training. Lastly, the advancements in time series analysis increasingly incorporate machine learning algorithms that can automatically identify the underlying patterns and best model parameters without much human intervention. This is facilitated through the use of tools and libraries that include autoregressive models, neural networks, and ensemble methods that combine multiple models to improve prediction accuracy. Algorithms like XGBoost and random forests are now being adapted for time series forecasts, permitting more robust predictions that can handle nonlinearities and interactions between multiple predictors more effectively. In summary, time series analysis is a multifaceted process that requires special attention to the temporal dependencies of the data. It involves stationarizing the data, visual exploration, decomposition of components, statistical modeling with ARIMA or its variants, and more complex machine learning methods like RNNs. Each step in the process allows for better understanding, modeling, and forecasting of time-dependent data. As machine learning continues to evolve, so too does the potential for predictive accuracy in time series analysis, making it an indispensable tool in many fields such as finance, meteorology, and economics. 3.9 Reinforcement Learning in Depth. Reinforcement learning, RL, is a type of machine learning that is distinguished by its focus on how agents ought to take actions in an environment to maximize cumulative reward. This branch of machine learning diverges from supervised learning, where the learning process is guided by labeled data, and unsupervised learning, which finds hidden patterns or intrinsic structures within input data. Instead, reinforcement learning is grounded in the interaction between an agent and its environment, learning from experience as opposed to being explicitly programmed for a specific task. In reinforcement learning scenarios, an agent is given the freedom to explore the environment, make decisions, and understand the consequences of those decisions through rewards or penalties, which inform the agent's future choices. The central component of reinforcement learning is the policy, defined as a strategy that the agent employs to determine its actions at any given state. A policy can be a simple function or a lookup table, but in advanced applications, it is typically represented by a complex model like a neural network. A good policy maximizes the expected return, which is the cumulative sum of rewards received by the agent in the long run. The policy is learned through repeated interactions with the environment and is refined as the agent gains more experience. The reward signal is the clear measure of success. It is the purpose of the agent to accumulate as much reward as possible, which drives the learning and decision-making process. Another crucial concept in reinforcement learning is the state value function, which estimates the expected return starting from a given state and following a certain policy. This function is essential for evaluating how good it is for an agent to be in a specific state and for assessing the quality of the policy being used. The goal of reinforcement learning algorithms is often to discover the optimal state value function, which would then dictate the best policy. The state value function, together with the action value function, which estimates the expected return following a specific action in a given state, forms the foundation for many reinforcement learning algorithms, including Q-learning and policy gradient methods. In attempting to find the optimal policy, reinforcement learning algorithms will often rely on different approaches for exploring the environment. Exploration is the act of trying different actions to discover new states and understand the consequences of actions. Exploitation, on the other hand, involves selecting the best known option to maximize the immediate reward. A balance between exploitation and exploration is necessary for an agent to learn effectively. Too much exploration can cause the process to be slow and inefficient, while too much exploitation can prevent the agent from finding potentially better strategies. Reinforcement learning algorithms use mechanisms like epsilon-greedy policies, where the parameter epsilon defines the likelihood of taking a random action versus the best current action, to manage this trade-off. Dynamic programming techniques, such as value iteration and policy iteration, are foundational methods in reinforcement learning used to solve Markov decision processes, MDPs. MDPs provide a mathematical framework for modeling decision-making in situations where outcomes are partly random and partly under the control of the agent. Such techniques require a full knowledge of the model, and while they guarantee convergence to the optimal policy, they are not always practical for real-world applications due to the computational cost and complexity associated with having a complete model of the environment. Model-free reinforcement learning algorithms like Q-learning and deep Q networks, DQN, enable the agent to operate without needing a model of the environment. These techniques directly learn the optimal policy or value functions from the experience collected through interactions with the environment. This approach is vastly more scalable and has been successfully employed in numerous applications, ranging from game playing to robotics. A significant breakthrough in model-free reinforcement learning was the introduction of function approximation methods, using deep learning to approximate the value functions, which allowed RL to be applied to more complex problems with larger state spaces. Deep reinforcement learning, which combines reinforcement learning with deep learning, has recently demonstrated remarkable successes. Deep neural networks can handle large amounts of high-dimensional data to learn effective representations and policies for challenging tasks, such as playing video games at a superhuman level or enabling autonomous vehicles to navigate complex environments. Algorithms like Deep Deterministic Policy Gradient, DDPG, and Proximal Policy Optimization, PPO, exemplify the advancements in deep reinforcement learning, where the algorithms can train policies in continuous action spaces and handle large-scale problems efficiently. Multi-agent reinforcement learning is another advanced facet of this field. While traditional reinforcement learning considers a single agent interacting with its environment, multi-agent reinforcement learning involves multiple agents simultaneously learning and evolving policies in a shared environment. This is reminiscent of natural ecosystems and human societies where multiple entities learn and adapt their behaviors while interacting with one another. This advanced technique poses additional challenges such as non-stationary environments, where the rules of the environment change over time due to the actions of other agents, but it allows for the study and simulation of complex systems where cooperative and competitive behaviors emerge. One of the major obstacles in applying reinforcement learning to real-world problems is the issue of safety and robustness. An RL agent may learn to exploit flaws in the simulation, or may make dangerous decisions when faced with situations it has never encountered before. Safe reinforcement learning aims to create algorithms that incorporate safety constraints and risk aversion into their decision-making processes. This is vital for applications in areas like healthcare, finance, and autonomous driving, where mistakes can have severe consequences. Research in this domain focuses on techniques to ensure that agents behave safely during exploration, and that policies learned in simulation can transfer to real-world scenarios without negative, unforeseen behaviors. Transfer learning and meta-learning are exciting research areas in advanced reinforcement learning. Transfer learning aims to apply knowledge gained in one problem to different but related problems, potentially reducing the time and data required to learn new tasks. For example, a reinforcement learning agent that learns to play one type of video game might apply some of its learned strategies to a different game. Meta-learning, or learning to learn, focuses on developing algorithms that can adapt to new tasks quickly with little data. This mimics human learning capabilities and is seen as a step toward achieving more general forms of artificial intelligence. These advanced techniques are indicative of the ongoing evolution in reinforcement learning, which aspired to build more flexible and general-purpose learning agents. Reinforcement learning is a vibrant and rapidly advancing subfield of machine learning that represents a paradigm shift from traditional static data-centric approaches. It offers a powerful framework for training algorithms that can learn complex behaviors across diverse domains. The ongoing development of advanced techniques in reinforcement learning holds promise for the creation of more intelligent, autonomous systems capable of learning from interaction with their environments and continually improving their performance over time. As technology progresses and computational resources grow, we can anticipate reinforcement learning to be an increasingly critical driver of innovation and efficiency in myriad applications. 3.10 Model interpretability and explainability. The concept of model interpretability and explainability is becoming increasingly important in the field of machine learning. Interpretability refers to the ease with which a human can understand the cause of a decision made by a model. Explainability extends this concept by providing understandable reasons to the stakeholders that describe how the model works. This requirement for transparency is vital in sensitive and regulated industries such as healthcare, finance, and law, where decisions need to be justified. Moreover, even in less regulated sectors, the ability to interpret and explain model predictions is crucial for trust and adoption. Model interpretability and explainability have several key benefits. First, they help in validating the robustness of machine learning models, ensuring that they are making decisions for the right reasons. Models that are interpretable and explainable are less likely to rely on spurious correlations that may not hold in the real world. This also means that these models are less susceptible to being fooled by adversarial examples or noise in the data. Second, they facilitate the detection and correction of biases that may reside in the data or the model, thus supporting ethical AI endeavors and fairness. There are various approaches to improving model interpretability and explainability. One approach is to use inherently interpretable models, such as linear regressions or decision trees, where the decision process is transparent. These models allow for direct inspection of their learned parameters or logic, enabling stakeholders to readily understand how inputs are being transformed into outputs. However, it is important to note that these models can become complex when dealing with high-dimensional data or intricate decision boundaries, which might reduce their interpretability. Another approach is to apply post hoc interpretation methods to complex models, such as neural networks or ensemble methods that are not easily interpretable by design. Techniques like LIME, Local Interpretable Model Agnostic Explanations, or SHAP, Shapley Additive Explanations, attempt to explain the predictions of any model by approximating the model around the prediction. These methods work by deriving importance values for each feature, indicating how much each feature contributed to the final prediction. The choice between using inherently interpretable models or post hoc interpretations generally involves a trade-off between interpretability and predictive performance. Feature importance is a common metric used to gain insights into which attributes of the data contribute most significantly to a model's predictions. Tools that rank feature importance can help explain the relative weights or significance of inputs for a given algorithm. By focusing on the most relevant features, domain experts can gain intuition about the model's reasoning. Additionally, analyzing feature importance can assist in model refinement by identifying features that do not contribute meaningfully to the model's accuracy. Another important method for improving interpretability and explainability is the use of visualization tools. Visualizations such as partial dependence plots or individual conditional expectation plots help in understanding the relationship between features and the prediction. These tools can also assist in identifying how features interact with each other within the model. Visualizations are particularly useful for communicating complex model behaviors to stakeholders who may not have the technical knowledge to understand the underlying algorithms. Model interpretability and explainability plays a significant role in model auditing. As machine learning systems become more widespread, the need for accountability and governance increases. Auditing involves examining a model's decision process and outcomes to ensure they are aligned with organizational or societal values. Transparent and understandable models facilitate the auditing process by allowing auditors to trace through the decision logic. Additionally, this level of transparency can help in identifying any instances of model drift, where the performance of a model degrades over time as it encounters new data. In some cases, the need for interpretability and explainability extends beyond individual model predictions to understanding the model's overall structure and behavior. Techniques such as sensitivity analysis or model ablation studies help in this regard, assessing the impact of inputs on outputs systematically. Sensitivity analysis evaluates how changes in input features affect model predictions, helping to gauge the robustness of models to input variability. Ablation studies systematically remove parts of the model, such as weights or features, to understand their effect on model performance and behavior. Model interpretability and explainability also raise legal and ethical concerns. In particular, the European Union's General Data Protection Regulation, GDPR, introduced the concept of the right to explanation, where individuals have the right to receive an explanation for automated decisions that significantly affect them. This regulatory requirement has driven significant research and development efforts to enhance the interpretability and explainability of machine learning models. Failure to provide explanations for automated decisions could result in legal and reputational risks for organizations.